Good morning. Am I audible?
Good morning, Sajid sir.
Yeah. Okay. Uh, so let me share my screen first. Okay. So is my screen visible and you can see the things what I'm writing online? Can you hear? Can you hear me?
Yes, sir.
Okay. Fine. Okay. Let me recap what we been through last time. Okay. This one, D box, and before that, okay, the smallness and bigness, D boxes, title, Jordan outer content, label outer measure. Okay, now I will continue the same with this one, and let us define some concrete different definitions based on the concepts we have defined last time. Uh, this Lebesgue and Jordan, if I would like to relate both, like Jordan versus um, Joe versus L. So, what do you think? Like, which one would be much stronger version, Jordan or Lebesgue? The things which we discussed, the main difference with both of them is the finiteness and countable infiniteness. Jordan is finite, whereas Lebesgue comes with countable infinite. So, if I would like to wrap me up in words, if you don't understand mathematical senses, like the definitions, whatever we provided here, um, the countable sum of um, D boxes, which covers the set which we are interested in, and we are choosing the least one, the smallest volume which you can cover on top of the given set with the finite this one finite D boxes, whereas here the same thing here with countable infiniteness. So what Jordan definition says, simply you can think of like uh, cover uh, cover the set in finitely, not infinitely, on top of it. Finitely meaning um, finitely many d boxes, and take the smallest, what do you say, smallest uh, total d volume, that is Jordan. It's not the definition, it is just to express the mathematical intuition, whatever mathematical, what is that? Yeah, this mathematical expression give us some kind of written intuition. That's what we are doing there. That next one, the Lebesgue, uh, the Lebesgue intuition says the same. It slightly differ. Cover the set in, instead of finitely many, we have to take here countably many. Countably, uh, countably many small d boxes, or you don't need to mention small, but of course we have to refine every time. So there is no expression to bring up what smallness it is, so we can write up without any loss of generality. Small d boxes, and take the smallest total volume, same total d volume. Okay. D here, D means the dimension which we are considering. The set may be sitting inside any dimension, like any D dimension. That is what D is. So, uh, what is this is actually doing? Where we are going now, right now, with these two conventions? Why this cover, or why this volume is our target? This is what we are looking at. If we suppose, let's suppose, if I have some set, the set notation in general we are keeping it y, and suppose if you have some set y, uh, subset of rd, if we cannot able to express either in Jordan or Lebesgue, what is the problem with it? Suppose if I don't express this y, why, as I cannot come up with this Mr. LD or Mr. JD with some volume, some smallest volume, then how do you look at this set? Can you think of any set which we cannot able to express with some uh, total D volume, smallest total D volume, so that which is this Y is covered by the smallest D boxes? If we don't express this Y as to come up with some cover, and which is the smallest totally volume, then what will the problem with that y? You get my point, right? Okay, I will give some clues or hints to understand what does it mean actually. Like, I assume that you already have been through the sequence of functions and the point-wise convergence of sequence of functions. Am I correct?
Yes, sir.
Okay. So, in the sequence of functions, what do? You have a sequence of functions fn, which converge to a function f. There are many ways of this path defines, like pointwise, through LP norm, through probability in stochastics settings, or there are a lot of ways. But let us confine our discussion with pointwise. That is a very quite obvious. Pointwise means you have a function, like let's say this is f1, and another function is a kind of f2, another function is f3, another function is f4, and so on. They are behaving different ways, and as n goes to infinity, these behaviors, the functions means the behaviors in the domain, they come to a band, they come to a kind of a closed band that is given epsilon band. Let's say this is epsilon neighborhood. So they don't go away in this band after certain stays. So all the functions stay within this, no matter they go in a line or they go in a straight line, doesn't matter. They don't go up. They don't go beyond that epsilon. So if you compare the same analogy with the sequences in real numbers, what do? AN is a sequence which converges to A. Let's say point A. That means what? In the real line, you have something. You have A1, you have somewhere A2, you have somewhere A3, and it goes on. After a certain stage, after a certain stage, what will happen? If that is converging to point A, that means there is A sitting inside here, and this is a given epsilon. So what do you say? The AN minus a is always less than epsilon for all n greater than certain stage. After this capital N, after this capital N, and your sequence like you have A1, A2, and so on, A capital N, A capital N plus 1, and so on. After this stage, all these numbers falling inside this neighborhood. Okay, this epsilon is your choice. No matter whatever epsilon is small, you give epsilon equal to you give 0.00001 or maybe a 10 zeros after 1, and you will find a stage. That stage will determine that no all the sequence points, all these comes under this epsilon neighborhood. That is what convergence in real sequence. That is what you write most of the time in the sequence definition. Sequence is converging means you write kind of this one. After a certain stage, everything falls within this small, within this neighborhood, no matter whatever epsilon choice you choose. That defines actually how close you are a. If you give 0.001, then you have a smaller you have a smaller capital N. That means maybe you can it convergence setting is epsilon. You can have a faster convergence because that is the wide you have chosen. 0.1 is much. You are not caring much error in that. So if you have choose epsilon equal to 0.0001, that means you are looking for the sequence should be somewhat finer, uh, to three decimal places, then you are looking for some other stage. After that, all the things fall inside that epsilon. So the same goes here too. Here, instead of numbers, you have functions. You have functions. Here you have function f1, you have function f2, you have function f3, you have so a lot of other things. Then what is happening here? Here you have function norm, that is fn minus f. Function norm is less than epsilon for all n greater than n. That means that these given epsilon, all the functions after a certain stage, these are all fall inside this epsilon neighborhood. But they don't escape. The same here. In the sequence, all these things fall inside this epsilon, this definition. So here it is a function definition. That's what like these functions, whatever the choice you choose, the sequence of functions, they under this ruling, this functional ruling, they converge to a particular function, that is we say f. That is so much fine. The sequence of functions, the sequence of real numbers, this you know it very well. Now I am coming up with the something called a D-box notion of volume of D-boxes, where it is taking care of this smallest arbitrary set, small the set which you have, that I am looking it for this measure of y. What is that actually? How I am going to connect, or how do we look at these two pieces um, together? That's what my point. So let me write it up in a different notion. So you understand the I just recapped our sequence definitions, and now let me put it together. Before that, like I just wanted to involve our thought process very deeply, so that uh, we almost touching towards the neural network context, but it is in the higher level settings where mathematics is abstract here. This abstract level mathematics maybe sometimes can't see immediately what is in the real line, I mean, real scenarios, but it takes a quite time to understand the connectivities, but be patientful. Okay. So are you okay as of now? Or before going touch something else, I just wanted to confirm from you that like the definitions so far what we have elaborated and discussed. Fine.
Yes, sir.
Yes, sir.
Okay. Good. Okay. Um, I don't want to write up the definition or the way I have accumulated this information on the screen, but I just wanted to construct or build from your thought process, not from already cooked up thing onto the screen. Okay. Let us go with a small task. I'll write up a sum set from the context of this one, the sequence of functions. Uh, this one, sequence of functions, whatever I just described on this definition, I just wanted to see. Um, and of course, here one thing, very crucial point. This is what I'm talking about is a point-wise convergence. That means point-wise convergence means there is a x hidden here, right? This f is just not a number, it is a function and it is acting on a domain. So you have always there is a x sitting there. For every x, it has to satisfy not just for one x. That means if it is the domain R, then every x you choose on top of this one, it should satisfy falling inside this epsilon neighborhood. It's not just for one x. It's not a single number. It is through entire domain. It should satisfy the domain of consideration, whatever domain you choose. Okay, that x is hidden. Whenever I am talking the point wise, that means that there is a uh, choice of domain is sitting inside. Okay, with that understanding, I just wanted to see set of all x's, those points. Okay, set of all x's uh, from where means from our in general RD, whatever RD, such that fn of x converge to f of x. You understand this one? The set construction. So that means that if you choose a sequence of function, you have some functions, some functional concept is there with you. You have the information, the first function, second function, and so on. Several functions are arbitrarily infinite, you can think of. It doesn't mean that whenever I say that it is converged to f, it need not be true for the entire RD. The entire RD it may not be. So some portion of the RD, it may be convergent. Let's say for D equal to 1, if you choose in the real line, so these your functions are coming into your choice of epsilon, these functions, your choice of epsilon into a certain domain. After that, they break up, they go out. But within this domain, this set construction, this region, but they are coming into this epsilon region. That means they are converging to your particular choice of f. Not what choice of f, but the behavior of those functions are converging to this function. But you don't think of what goes outside this domain. Whether they may go out, they may uh, they don't nicely behave with our choice of epsilon. So that is what I wrote here. Thus, some collection of x's, the domain which is coming to convergence of f of x. So what are all those points in our domain? The points, point-wise convergence, uh, the fn of x converges to f of x. That is the set. Now, this is so important. This is so important. Um, why that word important makes sense to me is this I wanted to establish into some way in the definition of convergence of functions. This is a set of collections, the points where fn of x is converged to f of x pointwise. Now, how I write up? Let me write up in the definition format. Um, okay, it is small space, but I will utilize below. This equality comes here. The set of all x's uh, belongs to RD, same thing, such that I just wanted to elaborate that one. Now I need to think of something in the way the epsilon sense, right? The fn minus f less than epsilon. I wanted to go with some kind of epsilon definition. Because the choice of the set it depends on purely how much epsilon you are choosing. So if you choose very small epsilon, maybe this behavior is not satisfying. Maybe some other part only will satisfy. Very small domain you may get it. If you choose very small epsilon, only few portions of the domain you may get it as your points where fn converges to f of x. So if you choose a little larger epsilon, maybe your domain may be larger because you have chosen such a wider convergence and I mean wider a range of functions they can come up. So this epsilon is actually playing a crucial role to determine what choice of what size of what accuracy of the domain you are looking for, what quality of points you are looking for. Do you understand? The quality means that the wideness sitting inside these functions are behaving. Suppose if you choose very small epsilon, like epsilon equal to let's say 10 rise minus 7 or minus 17, something very high precision. That means what? All those functions after a certain stage, all the points they are very close. They are very close within that. You can't you can't separate them very easily. They are so thick and they behave 10 rise minus 17. You say that okay, the two numbers are differ by 10 rise minus 17. That means you say almost they are same up to the order of 16. You can say so that means that is so precise function. But that is the choice you are choosing. So now here this epsilon is actually playing the role to determine these points. Now, I just wanted to give some notion for this epsilon, not to a given or not to a choice of your own. I just wanted to give some kind of, let me choose 1 by k. As our k increases, like their epsilon equal to 1 by k. That means if you choose k equal to 1, it is epsilon is just 1. That means you have um, error choice is 1. If 2, then 1 by 2, there's zero point 0.5, 3, 1 by 3, and so on. And or you're increasing infinitely many, I would say, as k goes to infinity. So epsilon is reducing the band, very thin band. So that's what my choice of that. Okay, so that is now uh, I will write up here fn of x minus f of x uh, f of x less than 1 by k. The epsilon I just replaced with this 1 by k, the definition. But now the k is a choice of my interest. I just wanted to go for k equal to for all possible choices, for 1, for 2, for 3, for 4, for n, and so on. So now what I do? So for every choice you have some collection. For k equal to 1 you have some domain, you will get it. For k equal to 2 you may get it some other domain. For k equal to 3 you may get it some other domain. So you have endless choices. So what would be the best choice out of all this? Suppose for k equal to 1 you get a point collection as b1. For k equal to 2 you get a point collection or domain collection. That means the points of um, the points at which the functions converges. Point 3 collection and so on. Let's say let's p1, p2, p3 are these sets. Like you can say this is a pk. The for You can keep it as a pk here, right, for a particular k. Now I just wanted to describe that. So out of all these p1, p2, and so on, pk and so on, k still goes to infinity. um, I want a best point collection. What will come? Maybe at k goes to infinity, maybe I don't have any points at all, as it goes to absolute 1 by it tends to 0. You may not get any two functions hardly behaves as the same in a larger domain. Maybe you may get a domain but it is very very thin or very very small domain, you may get it. So I don't want to bring that into nature, but somehow I wanted to come up with some best collection of points. You have all these collections. How do you choose a good choice of collection from out of all these domains? So again, there is a hidden thing. One more thing here. As you are written fn minus f less than 1 by k, even if you choose 1 by k, particular k, and you have for every k you have a stage, right? That means that you have this one. So for suppose the real numbers, these are all like a1, a2, a3, and so on. The n, okay, let's forget about a1. 1, 2, 3, 4, these are the k values, which are going for every k you choose. Okay, I'm sorry. These are not k, these are n. For every k you choose, you have a stage capital N. After that, they fall inside. These are all fall inside the 1 by k neighborhood. That's what, like these numbers. These numbers goes into place where the functions fall into the neighborhood of 1 by k. For every k you have something. That means like um, for k equal to 1 we have a stage n1. For k equal to 2 you have a stage n2. For k equal to 3 you have stage n3. The stages won't be the same for all the k's, right? So as it is going as well. Now you have choice of k's. For every k you have the stages, I could say nk. So you have the stage is actually determining after this the sequence points. These fn points are closer to f with the threshold 1 by k, right? That is what the threshold 1 by k means. The difference among them is fall inside 1 by k neighborhood. So this stage is also an important thing. This I can keep it as nk. Okay, now coming to top point. So now how do we determine this P1, P2, P3 and so on? So I combine all these three things together here so that you understand very clearly. So one way of saying, or maybe the best way I could say, um, the all possible choices of case, all possible choices of the stages accordingly with the k, they are falling inside. And if I choose the intersection of all these things, intersection, that means the best fit, the best collection of the best domain I will get it, where fn of x converges to f of x. P1 maybe because of k equal to 1, it has a larger, wider epsilon. It may grab a bad points into this convergence because I don't this epsilon equal to 1 is literally a bigger number, relatively I could say. As k goes to larger number, the epsilon size reduces. As the size reduces, the functions really start behaving nicely, converging to f. So if I choose that intersection, the intersection of k equal to 1 to infinity, and also there is something called union of the stages. I have to stage them. uh, Not that actually the union, yeah, union of n equal to the stages from n equal to, oh no, wait a minute. Yeah, the stages from n equal to 1 to infinity. This capital N is again there is a intersection in top of it. After after this stage, I have to carry with this n, right? This n still not yet arrived. Of, for all n greater than or equal to n. So now look at it. Whatever I have just explained, I just kept it in all together. So first one is the choice of k is determining, and the second one and third one are the choice of the stages. If you choose the stage equal to 1, and the intersection of all points after this number, and as n goes to infinity, the stage is also extending, and for a particular choice of k and particular choice of the stage, you are choosing the epsilon, and you are choosing the stage, and then you are intersecting all these points after the certain stage n. So what is happening after the certain stage n? These domain points are being collected. Huh? So this is the same definition of the points, the convergence definition in one context, I could say. Um, the collection of points. Okay, be clear with the notations. I did not say, I did not explain something new to you. This is, you already know it by the definition of what is the function sequence of functions converge to a function, but I wrote in a different lines.
Sir,
Yeah, yeah, please.
sir, for a K stage n is unique, no sir. How can it go from
Okay.
1 to infinite?
Yeah, this is a nice, good thing. So, uh, suppose here for every k equal to 1, mm, or for every choice of k you choose, and this stays, and I am not looking for this, uh wait a minute, like, okay, got it. And this one, this choice, as you said, it is a unique capital N. After a certain stage, all the things comes under uh, under this one. But the key thread here is the point wise convergence. When you are choosing a point wise thing, when you are considering into this point wise this x1, mm, so the key point sense of thinking is uh, it should come up with for all the x's within the domain. Okay, I will just go with some definition. Um, First one is intersection of k equal to 1 to infinity. This is the countable intersection, and well, next one is union of capital N equal to 1 to infinity. Next one is intersection capital N greater than or equal to the stages. Now, as you said this one, once we fix a particular k, some k, and now even when we fix a particular k, this stage actually determines how do you know that this stage is whether this one or someone. You have to search for the stage as you don't know the what is the stage, right? This n. So you are choosing n equal to 1 as considering it as a stage. You don't know it whether if it is, then you are looking go for it, and then n equal to 2 you go for this one, n equal to 3 you go for this one. For all those intersections you are ultimately come up with a particular point of n where all these intersections comes as a stage. These two together determining this n by searching from 1 to infinity. As you because we don't know the stage. If I give you k and you have to search for the stage, whether you don't know whether it is sitting at n equal to 1 or n equal to 2 or n equal to 3 n equal to 4 and so on. So for every choice of n you are determining a set, and then you are for every n you are doing an intersection. So then if we choose, let's say you choose n equal to 2, then what is happening? If n equal to 2 you choose, uh, let's say n equal to 1 you choose, you will get a bigger collection for all. Then what is happening here in the intersection part, if you choose n equal to 1 here, then you have to go for intersection of n greater than 1, then you do the intersection with the sequence, you will get a large collection, right? Then you choose n equal to 2. Then you will get a, for all n greater than 2, you will get another large collection. Then you continue this one, n greater than 3, and you will get a large collection. Okay? Intersection of all these three, all these stages, this capital N, then what it is determining? It is determining the uh, 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 it is determining what capital N, what capital N here, this one, this for every choice of n equal to 2 n equal to 3, as it goes to infinity. So then you keep continue this one till uh, that that capital N for all possible stages. Then you are searching for that n stage. So this one n greater than capital N. So this n is literally you are keep increasing at where the functions uh, comes under this intersection of all these stages. Like you will have a particular domain as n equal to 1 because you have not chosen any stage. After the certain stage you have chosen all the natural sequences 1, 2, 3, 4, and so on. Then n equal to 2 for all the choices of this one. N equal to 3 you are keep uh, keep on increasing one with the other. Then then for every choice of n, and you intersect all of them. When you intersect with this one, with this one with then, these are all with cancel outs means they don't come as a common. And after certain stage what will happen, because of this k is sitting inside, this k 1 by k is sitting inside, this intersection comes a stable state where no matter whatever n you choose, whatever large you go, this capital N, that is what intersection of n equal to 1 to infinity, whatever large you go, doesn't matter, they come as a particular fixed, rigid, solid, um, the stage points, the intersection domain points, which will be the consideration of our the x for that particular k. Again, you choose another k. Again, you go for the same uh, filtration process. The filtration process brings you into the intersection of all those searchings. Then you come up with a final the domain for the one way of saying that fn absolutely converging, or fn is point-wise converging to f in this way. Yeah. Any discrepancy? Hello? Yeah.
ఎవరమ్మా నువ్వు
Sir, can we do any example?
As of now, we don't do any example here. You can, because it's a functional spaces we are discussing in RD. It is a abstract sense, but you can try up with your real course example. If you take one, uh, you take some sequence, simple sequence like you can take fn. You can take some sequence 1 by n. You simply start with this one. Simple 1 by n sequence itself 1 by n. Is it a convergent sequence? So that means,
Yes,
um,
sir.
I mean, this 1 by, I don't say it as a 1 by n, or 1 by nx. 1 by nx, because the functions are sitting inside like it is a sequence of functions. Like f1 is here 1 by x, f2 is 1 by 2x, f3 is 1 by 3x, and so on. Your fn is 1 by nx. So where they are converging, to which function it is converging? Some function f. What is this function? You think of it.
Zero function, sir.
So they are converging to zero as n goes to infinity. Yes, tell me, is it zero, or do you have some other answer?
Zero, sir.
Okay, then now think of what is the domain? The domain which takes you to the zero. the set of all x's, for what x's the fn converge to x, sorry, f.
Sir, all were real number except 0, sir.
Okay,
Check.
all real numbers except 0. Now, um, can you bring that intuition into this definition, this set notation? The you said like this is r difference 0. So now that r difference 0, can you bring that into where is our definition? Yeah, this one. So if you evaluate this one, it should be equal to, for that particular sequence in R1, not RD. It should be R difference 0. Are you getting it? You just check it out. It's kind of a, uh, a simple task, but I don't think of it as a cumbersome task, but you can get them. So yeah, it is not about the sequence where it's not about the sequence of functions converging to a function. It is about the domain we are interested in. Now I am moving ahead to understand the conceptual things behind sitting inside this one. So why this one? Like my interest is this set is a kind of mm, so the domain of uh, this one. How I could able to know this set is a proper behavior or collection of points, or uh, um, uh, why even in general nature we don't have the functions of this nature, like this 1 by nx or 1 by x or nx by nx plus 1 or whatever, like the functional formats in general we don't have them in nice things. We will have them in a data. So I quickly used the word data before. I will use a little later. Keep it aside. Then I will talk the data in terms of mathematics. For time being, just stay with abstract math. So in general, we don't have these functions with nice formats. You have some raw information you have, and those are all, whether you don't know whether they are converging or not. If they are converging, what is the area where they are converging? That is your choice, that is you have interested in. And you have to go with the rules of um, the for every choice of decisions you make, to look at the domain of interest which is satisfying these information records, or tending or generalizing to a particular point, particular function, and also accordingly where it is. That is so important. Like why important? Like it is the data actually. It is the behaviors of the data on different contexts, that is n. And are they generalizing? Generalizing means, are they come up with some sort of generalized formulation, so that I can use this generalized formulation for entire, as my rule, instead of just for one instance. That is what machine learning starts looking for, generalizing of the functions. Okay, that is, I will come back to it once we reach that point. Now, to talk in the mathematical language of this set, now I would like to know the behaviors in this set, or important to know what behavior of this set is having. So you could see some behavior. There are crucial things were here. One is the point one is countable intersections in that domain collection. Countable intersection, and the second one is countable union. Countable unions. Okay, these two are the key things because we do countable intersections and countable unions. So the algebra is here with the unions and intersections of sets. So if they don't behave unions and intersections very properly on these sets, then it would be a problem. Why it is a problem? So, meaning like in group theory, we have studied something called like a closure property. You have something inside, you have an x, you have a y, you apply a operator on top of it, x star, and y, x star y is also sitting inside, then is okay. But whenever you do x and y, you apply some star and it is going outside of your interest, then you don't think of that is a good thing. Why it is not a good thing? Because you don't have control over your domain what you have with you. So to have a good control of yourself, you always look for some kind of operations, whatever operations you choose, that should be satisfactory. It's the closure property. It is so important to maintain, to stay within the same world. You are not going out of the world. When somebody is doing messing up with something operating, and suddenly the result is going out of the world, then it is pointless to discuss such points, such domains or worlds. So that is here arbitrary unions and arbitrary intersections which we are using here, that especially should satisfy the closeness uh, properties. That is what like we discuss now. So now what is my target is the measure whatever I am talking, the Lebesgue measure mu, the mu star uh, LD of union of n, okay, not n, I equal to 1 to infinity some. Okay, let me keep a i's. If I wanted to write up equal to summation, the sum of the d boxes, I equal to 1 to infinity, the mu star LD of AI. You understand this one? It is so satisfying thing. Uh, the measure on the set, some real number function. It is a function. Mu star LD is a function which we are assigning each set to a number. Union of all those sets equal to sum of the measures of those sets. The measure of union of those sets equal to sum of the individual measures of the sets. So if this is there, then this set is so nicely behaving, and also you can say that AI intersection AJ equal to empty. The boxes are well separated. They are not having any overlaps. If you have some overlap, that means that you are accumulating this one and this one two times, and you are summing it up. You are summing it up means the infimum definition, whatever we choose, then that is, uh, of course, not a good idea to take such things, because the overlap brings the volume of the D box into consideration twice into your infimum collection set. So you have to take smallest one, so that all those things should go tightly packed up like this. The D volumes are tightly packed up so that they don't have any intersections. So this should ensure one thing. This we say uh, some countable additivity. Countable additivity. The it is satisfying measure of unions of sets equal to sum of the measures of the sets. Countable additivity. To ensure this countable additivity, we need some kind of uh, robust world or set world, that is uh, that is a kind of name. Maybe your first time you are listening. What I am going to say now is called sigma algebra. Have you heard before this sigma algebra?
Yes, sir, in stochastic calculus.
Okay, then you have an idea. Sigma
So
algebra.
we have done Borel sigma algebra, Borel sets.
Oh, okay. Yeah, Borel sigma algebra. In which course?
Stochastic calculus.
Stochastic last semester or this semester?
No, sir, ongoing.
Oh, okay. It's ongoing. That's good. That's good. Like, okay. Then my job is easy for now, to because you already know the definition. So, but I will go with the context what I am defining. But explanations are straight away because you know it already. So the sigma algebra. So can you, as you know already, can you define from your point of view what is sigma algebra? Just in our words. It doesn't mean that like you should uh, write up or in the textbook context. It's in our own words. You define anyone. Okay. I, I define sigma algebra in my this one like. um, So sigma, suppose you have some abstract set x, let's say some x. Um, what is the collection of all subsets of x? That you call it as a power set of x. Of course, power set of x is obviously sigma algebra. That we will see later. But what I want to do, instead of power set of x, I need uh, some collection of sets, subsets, like let me choose uh, the notations are quite tricky. Sometimes they overlap with some other sigma algebra. So which notation you are using for sigma algebra? Space.
So sigma symbol, dash, and algebra like.
Okay, uh, that is fine for. Okay, I think it's disconnected or what?
Sir, we used F symbol.
Okay, F symbol. For me, I'm just thinking, did I have any sums? I use it to go mostly sometimes with M, sometimes with A, this one, script letters. Okay, I'll just go with A. Language doesn't matter. A. Yeah, if I may use it for some other purpose, that's what I don't keep that as. Right? Okay. This A is some subset of this power set of X. Some subset of power set of X. We say this, so, the subset of power set of X means power set of X is the sets of all possible subsets of X, and we are having some collection of subsets. Those subsets should satisfy few properties. That is, one is like the empty set and the whole set should be belongs to that A, and the second one is if a set A belongs to this collection, then the
A complement should also.
the yeah complement of A should belongs to that one, the entire set. Third one, if you have countable collections, that is, I just keep A1, A2, and so on, the countable, uh, infinitely many countable belongs to this sigma algebra, then it implies union of countable union of all these must be also belongs to the same. So why this one, this algebra? Then what it is doing actually? Why the sigma algebra so stressful or stressed here in this context? Suppose if we take some other set which is not sigma algebra, some collection, then what is the problem? That question you should arise, like the collection of A's which are not satisfying these rules. One of the rule is failing. Then what could go wrong with this collection? Can you, as you know already sigma algebra, so can you think of in that sense? Or you may take it as a thought process and you can think later as well. What is the wrong uh, if the collection doesn't go with sigma algebra? So actually, I gave the sigma algebra definition at this point of time uh, to deal this set. To deal this set. So to deal this kind of sets very properly, we need the sigma algebra definition here. Countable unions and countable intersections are the key. So,
Sir,
yeah,
as we have read, like sigma algebra use it to pick the best subsets given a set. If we want to pick some best subsets, we can use sigma algebra.
okay. Here the context comes like the best subsets are the key. Like in which sense the best you say that the best is the word is a way many ways it can be. It's again yeah, many ways of defining the bestness. So that is where we have the underlying algebra. We have this actually the bestness or worstness or whatever. that defines this by this collection. This you have a lot of collections. It's not a single collection. There are a lot of choice of algebras. They define a own world by keeping these rules satisfying. Every sigma algebra is different from other. That is the nature of the sets which are holding the persons or the points or the items which are holding. They define their own definition for that sigma algebra to define its own bestness. The bestness of if you ask me this sigma algebra and A1, and if you give me some other sigma algebra A2, they two are different worlds. So the bestness of the collection of choice is depends on the context of sigma algebra you choose. And even though if you take the entire whole collection, it is itself a sigma algebra. So, this context where you are dealing, in which metrics or which kind of choice of sets you are dealing, that defines its uh, own rules of its own world. So, now coming to a kind of a new setting, like from the sigma algebra point of view. Uh, this one, what I could say, I will go with some more points, then we will come and together we will work it out, putting putting several things together, and we'll discuss further in the context of especially the convergence of sequence of functions. Okay, now I will ask with a question. So far, like, don't think of too much at this point. Like, it takes time. I have defined a kind of uh, like measure, and talking something like uh, convergence of uh, sequence of functions, and now uh, talking uh, sigma algebra. Hmm? These three pieces will uh, uh, we'll look at all the three things together in much maybe next classes. But now I will go with some kind of. I ask you some questions. Some questions. Why I have uh, measure that is independent now? As of now, I think you think them as a different individual pieces. Like measure, how measure is what is the measure do with convergence, what is the convergence of sequence of functions to do with the sigma algebra, the what are the connections among themselves. I just wanted to know from our way by asking straight questions like now I'll give some questions, you think on them. Why measurability uh, measurability uh, matters uh, in convergence. That is, once you know this one, why measurability comes into the picture of convergence, then automatically it brings sigma algebra into it. Okay, let us think of in another context, like if we have the definition above, we have defined like set of all x belongs to x. I think I kept this one as RD, but from now I am replacing RD with X, so it is so abstract. And the RD can be a particular thing. So now Fn of X does not converge to f of x. Conversely, set of all x's, earlier we have seen that set of all x's where Fn converge to f of x. Now Fn of x does not converge to f of x. Okay, so now think of that one and think of this one, and now why the measurability comes into the picture. And if I want, let's say this one is some set, uh, let's say the name I can keep it as um, B C E D. Okay, I will keep it E. Uh, this E, um, measure of, suppose if I want measure of E equal to 0, subject to measure of E equal to 0, that means um, what is the measure of E? This measure of E means what? Mu star LD. What does it mean? It is quite crazy. You can't able to tell the measure. You have a set, but you can't able to tell the measure. Yeah, but you can say the measure is 0. That there are there are three things you can say. One is measurable. A set is measurable. Another one is um, not measurable. Another one is zero measure. Zero measure is of course measurable. This one is of course measurable. If you can able to measure, then only you can say measure. Zero measure. Measure zero. So can you give some definition, some example, so which can give the measure zero, so that it will make you understand what is measure zero sets. Suppose in the real line you have q, the set of all the rational numbers. What is the measure of it one? What is the measure of this one? Hello, hello, measure. It's a measure zero. Think of it. Why it's measure zero? It's not just for Q. It is any countable set is always measure zero. Lebesgue measure especially, not the Jordan content. We think of in the infinite sense, not in the finite sense. Yep. Why can we say this one? Simply the Q is union of n equal to 1 to infinity. You have you have all the numbers as a singleton sets, you can say. So measure of each singleton set, you have seen that like sum of uh, okay, you wanted to see measure mu star ld of q equal to mu star ld of union of n equal to 1 to infinity un. These are all singleton sets, and they are disjoint one with the other, which can be expressed as sum of mu star ld of uns n equal to 1 to infinity. So each one measure is zero. So So Lebesgue measure is zero for all these sets. Now, zero measure is okay. We have a measurable definition. A set is measurable, or if we can able to come up with something. What is not measurable? A set which is not measurable. This is so tricky. Think of it. Think for a set which is not measurable. This is important. Like and let us understand the context of sets in the definition of the measureness. The how do we the D box measureness. So that will lead to a point where you have to deal with the sets very absolute way. So that forces you to think on the sigma algebra. Without the sigma algebra, you can't say the measurements. So we will connect all the three pieces, these things. Why sigma algebra, why convergence of sequence, why measure. Before that, you should know in our stochastics, even the measure is also there, or you are just knowing the measure from without measure, the sigma algebra is dealing. Hello, you are dealing measurable space in sigma algebra, or only just sigma algebra?
No, sir, we are not studying measurable space.
I mean, like currently you are doing stochastic calculus, right? Where I think measure is also there. That's what I'm saying. Like, are you studying measure along with sigma algebra? Hello, because
So till
some
now, sir,
okay, maybe you will come up like because
Sir, we have not studied deeply, but Sir said Leibniz measure on interval. AB is B minus A, and then we continue.
okay, so the just a measure thing. Yeah. So the sigma algebra definition is actually for the measureness only. The definition motivation is measure. So that is why the people say this one the when the sigma algebra A or F in our case maybe this A sorry and this not with A, this X with this A sigma algebra is called uh, measurable space. Measurable space. This is so important. That is sigma algebra is coming into the picture. Yeah. So why we are saying it as a measurable space is for some reason. Okay, I will just go with a few questions. You think on them as this is the point where we have the connections need to establish. So I will write some few properties on the measure so that you understand them a little bit good way. Let me say. Um, First property of the measure so far we have defined like mu star LD of empty set is zero. Empty set measure is zero by the definition you can think of. Next one is mu star LD of uh, LD of set, let's say A less than or equal to mu star LD of B, two sets A and B, if A is subset of B. The third one, um, mu star LD of the measure. You just verify with the definition. You will satisfy actually. I'm just writing it up. Mu star LD of A plus singleton element A, the set with A. You understand the set A. This is the element A. A plus means you are adding every element with A. That means A plus A equal to, you can answer me right now. What it could be? If you add A plus A with A plus B, LD of A is less than or equal to summation of n equal to 1 to infinity mu star LD of AN. Oh, you understand? This is very clear. Why less than? Can you give me a meaning? Why less than? I already discussed with 10 minutes ago. Why they are not equal? Earlier, I think I have shown you something called equal. Now I am saying brings the lot of measure. The measure can be accumulated double. So it, the right hand side can be a bigger one if they are overlap. And I just explained some about the Q1 mu star LD okay. So You can say this answer, right? Mr. LD of RD for any D. The measure. Can you keep the boxes on top of RD and sum them up? Or not sum them up and get the minimum of it. Yes. Then what could be that minimum? That can be infinity only. There is nothing to think on that. On that. Can you see my screen? Sometimes it is switching off. Keep repeating. Hello? Can you hear me? Are you there?
Yes, sir.
Yes, sir.
Okay, fine, thanks. Okay, yeah, a quick question, or you can think on this ones now. These properties are straight away from the definition, nothing to think too much. So these properties are now. I will ask one fair question. Which is little addition to the earlier one. Um, can we have a function? Can we have a function? Let's say the mu. I'm not saying whether it is LD or something mu, such that power set of RD uh, goes to 0 to infinity. That means that the mu is a function which is mapping every subset of RD to a real number. Not just real number, it is positive real number. Okay, non-negative real number, because 0 is also we are keeping it, such that such that what are my criteria? The first point is the mu with the set A must be equal to volume of D box of A if A is subset of RD is a D box. If it is a D box, then mu of A must be volume of the D box. Okay. Second point, the mu of A must be less than or equal to mu of B for subsets A comma B of RD with okay and okay with A is subset B. Second point, that is these three conditions should satisfy. First one is, if you are assigning a subset of RD, if it is a D box, then it must be equal to volume of the D box, and the number must be volume of the D box. If two of the numbers are one with the other, if they are related with less than or equal to, then they must be equal to A subset B. And third one, here, okay, I can keep it as subset or equal to, doesn't matter, no problem. The third one is the mu of union of n equal to 1 to infinity an must be equal to summation of must be equal to, okay, n equal to 1 to infinity mu of each each measure if uh, ans are pairwise disjoint. Yeah, that's it. Now this is the question to you. Now think of, to answer this question, to answer this question, think of sigma algebra, think of the measure definition, how they are related. Okay? So this is the forceful thing to bring the sigma algebra into the definition. If it is now you can think of like instead of this one power set of RD, you take some other X and some sigma algebra here. Instead of just P of RD, think of some sigma algebra and how it is behaving. If it is not a sigma algebra, then how these three properties uh, are framing. Uh, these are all like kind of they are not mathematical like proofs or theorems. They're just to understand the definitions and the context behind how like you can think of like we just follow definitions, we take it granted and we use them, but definitions don't come just like that. Definitions forms based on seeing a natural observation, and it becomes as a rule. That rule we are keeping it as a definition and we are taking it granted after certain time. But you should know what is the motivation behind the definition. Why these properties, so and so properties became as a definition, became as a rule, became as a kind of a constant or thought process, which is developing the further down the theory on top of that definition. So just not to take it granted, to understand why sigma algebra, why these things are really built up from the scratch. Okay, the too much abstract will I will stop maybe this week, either two or I think we have on Monday and we have on Monday and Tuesday, right? Monday one lecture and Tuesday two lectures. I think three lectures. After that, I slowly move the abstract things into the real next week, further next week, not the next week, further next week. Okay. So another 3 to 4 lectures we will stay in this abstract sense and understand why this measure, why this abstract sigma algebra, and really understand why neural networks are uh, built on top of these definitions. I can't imagine neural network without sigma algebra, but that is the theory says, the theoretical ground. Because of measure, the measure, without measure, there is no technology. They are all working because you are training a lot of data and by neural networks or something, some other model. Because of there is a measure always involved. Without that measure quantifying the data, you can't say anything. There is no way of dealing data with algorithms without quantifying the metrics and the relations between the data. So the quantification needs a strong theory or strong basis uh, where those comes from. That is the origin. It is lies in this measure theory. Okay. So if these definitions are not exist in the world, if these definitions, the sigma algebra and measurability things, then we wouldn't have seen this advanced technology called uh, artificial intelligence or neural networks. So that is why I'm stressing these 3 points: the measure, the space of functions, the space of sets, the sigma algebra, and further down the line, few more things were there. I will add up little later. So these are the building blocks for our uh, neural network or current the emerging technologies or growing technologies. But as mathematics grown, as you are from, you should know these things at least in shallow level. You may not go into the very deep research into the measure theory. Of course, you can do it as you go for further higher studies in the research line if you want. But at the moment, I just wanted to convey you that how this core abstract mathematics is the cause for our current neural networks. Okay, so I hope I will share this one so that you have a rich, good look at all these things. Uh, for further reading, I could say I don't have any a concrete material or a concrete textbook on this subject. Um, I think better you may use the definitions. Here there are no big things here. You just use Google search, or you may use ChatGPT with careful things, because sometimes it gives wrong intuitions and meanings that you should cross verify. Okay, so have a good understanding of these conceptual items, which makes you the road much clear understanding of why neural networks are working. So if somebody asks you, oh, why the training process is working, why the computers are learning, the answer is that today's lecture completely, but that you may not see at the moment, but that will you will realize soon. So wait for that moment. Yeah, that's it. You have any questions, you ask me, then we'll meet Monday.
Sir,
Yeah,
sir, measure of countable set is zero, right?
measure of any
From
countable set is zero.
mathematics it is okay, but I'm not getting any intuitive idea how
You are not
measure on
getting
some any intuitive idea behind it. Like how can measure
uh,
on some set zero?
measure on countable set, especially zero. Countable sets, like you think of like uh, the measure, the definition of the measure, what we are doing, we have to keep it. The countable sets, by meaning they are discrete, they are isolated, right? They are
Yes, sir.
discrete. Countable means you can able to separate them out. So now think of the D box construction. So what is the smallest D box you can put it? The singleton Z box. That point itself, right? the point itself, then what is happening? The each point have a measure zero. Single point is always a measure zero. So no matter whatever countable you think of, like irrespective of what it is, any countable set. Why that is because the infimum, what we are considering, the infimum of uh, the the D box summation, right? The sum of the D box um, I equal to 1 to infinity. This one is the thing. This is a countable sum. If whenever there is a countable sum with the countable things and each point is zero, then it is informate zero itself. But suppose if I don't say this one is not a countable one, if I say that it is a uh, it is sum over some index set, some I belongs to index set. Index set is I defined ix as a kind of uncountable set. Then that would be different because of the definition where we are using the Lebesgue sense. The Lebesgue sense definition, we don't use this index set as a uncountable one. It is we always take it as a countable set as Lebesgue notion we are following it. As we have countable sum with the countable sets, so you can always discretely brings the things. But now countable with uncountable ones like intervals 1 to 2, then there is a problem. Like a problem in the sense like you have uncountably many things. So then the definition of this one brings you the closed boxes, the D boxes. If you keep any D boxes here, no matter whatever D box you choose, they have the full number of points are sitting there. So the length, the volume, whatever we are taking, that we have to take into the consideration. So the intuition comes from the nature of the set and the nature of the definition. The nature of the definition is following a countable collection. That is why it is so important the sigma algebra definition. It is a countable union. There is you have a definition sigma algebra union of I equal to 1 to an. This is a countable union. If somebody says that I belongs to ix. Ix means that uh, this can be index set. Index set is can be anything, countable or uncountable. If it is uncountable index set, then sigma algebra fails there. So these two are the key connections, whether the sum is countable or sum is uncountable, whether the collection of the points and the collection of subsets you are considering, they are countable union or uncountable union. So the countable union has a nice behavior with uh, collection of subsets which from the domain where you brought in. So from there, the definition of Lebesgue sense are literally they are connected. Countable union of subsets, countable sum of the measures. So this is the key point, the connection between them. So that is why the countable thing. So you ask yourself the questions of several ways, like the contrapositive way. Why? If it is not, if it is not a countable, then what is the how can we define a measure on some sets? Like keeping one with fixed, like The keep the definition of the Lebesgue measure is same, and now think on that like different sets like what is the measure of Q, what is the measure of R difference Q. Even for the Q, you can think of like what if it is finite, like uh, the let me say Q intersection 0 comma 1. Okay, what is the measure of mu star um, j comma d, not L, j comma d? Can you answer this one? There is a difference. What is the mu star L comma d q intersection 0 comma d? If you answer these two things very properly from the definition of j and from the definition of L, it will convince you the measure on different sets with countable things. These are countable. Intersection is a countable. So, do you think both the answers are zero?
On J it is finite and on L it is zeros.
Okay, J it is finite. What is that finite number? Think on these answers so you will get them very clearly.
So it is not defined on J.
Oh, J is not defined on that. Like, I don't agree with that. Think is the clearly defined. And think of the sets where you can't say the measure. So it will brings you. It will why these exercises are so important, or thinking is so important, that it forces you to sigma algebra. Sigma algebra is a safe zone, I could say, a safe zone where the largest collection of subsets in a box these measures behave very good. Measures are well behaved. That point you should reach by trying it out different examples and different contexts on this Mr. LD, and where it is not defined, and if it is defined, how the definition is bringing that number either zero or non-zero, and why for some sets we can't able to define. And if I eliminate all those subsets where we cannot define, then the nice collection of sets, and how they are, what is the nature of those collections after removing these non-defined non-defined measure set, I mean not measurable sets. So that brings you sigma algebra. So the path to the sigma algebra is this one. So you are putting a safe collection of subsets where it is measure is behaving very good. Measure is following its own rules, like whatever rules we framed here, like these rules are these rules, they don't have any problem with these rules by convention. Our they are they, they are real number sense. We can think them as these rules are well off, and to bring those rules, what kind of collection of sets are the world we should choose that these rules behave very good. That is where sigma algebra comes into the picture. So for that you need to think too much on this various collection of the sets. Okay, let's stop here. And yeah,
Sir, is it one for Jordan Q interaction 0?
this one, Mr. JD, this one.
Yes, sir.
Okay, can you say reason why? Why it is one?
We can cover it with interval 0 on itself.
We can cover it with interval 0 comma 1. Okay, then why can't we do the same with this one? We are almost close to the answer. I'm just asking. Can you, okay, another way of asking, can you give two, uh, uh, I mean, mu star JD for this one? Okay, I will write it up separately. Mu star J comma D of Q intersection 0 comma 1 equal to, we have some kind of infimum of this so and so this one, the here the sigma I equal to 1 to some finite number k. Can you give for k equal to 2? Can you give a cover for k equal to 2? I'm not asking that is the answer, but some k equal to 2, can you give it? Some cover. What is that cover and what is its measure? What are all possible? It need not be the single one. For k equal to 2, can you define the union of two pieces like this? And what could be the measure of it? Only two covers. And
0, 1 by 2, 1 by 2, 2.
0, 1 by 2, 1 by 2 to 1. Right? And with the intersection with q, of course. Right now? Is it?
Yes, sir.
Yeah. Now it need not be the same thing. Like 1 by 2, I can go with 1 by 4 to 1 as well. There's no
Yes,
matter.
sir.
Yeah, problem, no problem. And now if you go with the measure, what is going to be happening? If you wanted to follow the definition of the mu star, then you need a finite cover all the time. So you can't go by individual boxes like earlier in the Lebesgue. In the Lebesgue, you can go by individual points and you can go with infinitely many countables. But here we have only the finite things. So you have to go with the finite cover, that is q intersection 0 comma 1 by 2 union q intersection 0 comma 1 by 2 1 by 4 comma 1. This measure of this one is just 1 by 2 plus this one is 3 by what is this 3 by 2 intersection 1 by 4 comma 1, I think it is 3 by 4, right? This measure is 3 by 4, so it is more than 1. And of course you will get the measure if you choose the partition as you said earlier 1 by 2 comma 1, then 1 by 2 plus 1 by 2 1 by 2 will come. So the measure is here is 1 for the Jordan sense because of the finiteness is causing you the problem. The finiteness is allowing you to choose this as a whole piece as 1 by 2 and this whole piece as 3 by 4. Of course, if the definition gives you the infinite sense of countability, then you can bring each box into each point. That is not possible here. No matter you cannot cover this one any piece with a finite number of boxes. You have to keep a box which is a single box for the entire thing. Can you cover up with a finite number of boxes? I mean, for each individual point, it's not possible as you have only limited number of boxes. You have to fix the k. So then you have to go with as many small things for k equal to 10 you can choose. You can bring it down this one into the several pieces as intervals only, but you cannot keep it as a single ton boxes. That is where the definition is finite, is restricting you not to go by the point by point box. So then you have measure ultimately is 1. The infimum is of course it is more, maybe greater than 1, even if it is greater than 1, but the infimum definitely brings to 1 only. But whereas Lebesgue sense, no, it is 0. Okay, I think you understand, right?
Yes,
Yes, sir.
sir.
Yeah, it's clear now. Think on this one. The sets where the measure we cannot define like one or zero. We can't say anything. What set it could be, and how do you come up with that? Like how bad the set it is, and why the where can we go for the good collection of sets where measure is not have a problem, and finally convince yourself that that is only possible with sigma algebra is the safe zone. Yeah, that's you think on. Then we'll discuss further in the next class.
Okay,
Okay.
sir.
Yeah.
Sir, we have sir, club session also, sir. So,
Sorry. What?
sir, we have club session, sir, from 12 p.m. Can we
Yeah. Yeah.
end the class?
Yeah.
Okay.
Now. Okay. Yeah. I am closing it.
Okay.
Yeah.
Okay. Thank you, sir.
See you. Bye.